Right. Our next talk is a tech talk, Modeling Interaction Dynamics to Influence Human AI Collaboration in Decision-Making, presented by Professor Ming from the Computer Science Department here at Purdue. Professor Yin has received a lot of accolades as of late, as every time I seem to open up Purdue News, she's being recognized with another honor. So it's thank you for taking time from your schedule to come and present your research.
Cool. Thank you very much for the introduction, and I'm very happy to be here to share with you some of our recent research on modeling interaction dynamics to influence human AI collaboration in decision-making. So as we all know, in the past decade, the AI technology has made remarkable progress, and it has also fundamentally changed how decisions are made today. In the past, given a decision-making task, usually it's a human who will process this task, deliberate about different possibilities, and make final decisions. But nowadays, because we have trained AI models to uncover hidden insights from the big data, given the same decision-making tasks, those decision aids powered by this AI model can analyze the task and provide a wide range of decision suggestions. And these suggestions may include the recommended decision for the human to take, and it may also contain additional assistive information like the AI model's confidence or AI's explanation to its recommendation. Well, all of this information will later be presented to human decision makers to assist them in making a wide range of decisions, including decisions related to cybersecurity. So if you think about it, nowadays decision-making is essentially becoming a collaborative process that is jointly completed by human decision makers and the AI models. And why we need this kind of human-AI collaboration in decision-making? The promise is that human and AI each have their own respective strengths, and by collaborating with each other, they can complement each other. So as a team, the human-AI team can achieve a higher level of decision-making performance than either party alone. However, in reality, we actually find this kind of human-AI complementarity is rarely achieved in practice. And naturally, we wonder why this is the case. So in the past few years, my group has conducted a wide range of empirical research to better understand how exactly do human decision makers make use of these decision suggestions made by AI models. And we actually find a few important limitations in the current interaction dynamics between human decision makers and AI. For example, we find that humans often struggle to make effective use of all this kind of assistive information presented to them by the AI model. Many researchers, including ourselves, have found that when AI presents its explanations to human decision makers, human can hardly make best use of that explanation to calibrate their trust in the AI model. And moreover, we also find that when humans decide whether to trust and adopt the recommendation provided by the AI models, their adoption of the AI is heavily shaped by their cognitive biases, which may actually lead to inappropriate trust and adoption of AI recommendation. So given all these limitations of human-AI dynamics, naturally we will wonder how can we overcome these limitations and improve the collaboration outcome between human and AI in decision-making. I will argue that one promising approach is that we should redesign the AI-based decision aids to adapt to how humans actually interact with them. And in order to do that, one of the important steps to take at the very beginning is actually to obtain more computational understanding of how exactly do humans interact with AI. And ideally, we want to quantitatively model this interaction dynamics. For example, as we said, humans have a difficulty make sense of the information provided by the AI models. So maybe we should try to model how exactly humans will react to different pieces of information presented by AI. In addition, because a human may be subject to many different kinds of biases in determining whether to adopt AI's recommendation, we probably want to have a better understanding of that process as well. We can model how exactly a human will determine whether to adopt AI's recommendation or not. And once we have all these models, we can start to think about redesign the AI-based decision aids. And this kind of redesign can be delivered through the redesign of human-AI interaction protocol in the sense of how to provide provide AI recommendation to people. And it can also be delivered from by just changing the AI model underlying the decision aids all at once, meaning that we can fundamentally change what kind of recommendations being presented to human decision makers. So in today's talk, what I would like to do is to give you two examples to illustrate how the computational models of human AI dynamics can actually inform the redesign of AI-based decision aids and eventually influence the collaboration outcome in decision making. So let's start from the first example, first project, in which we modeled humans' reaction to different information presented to them by the AI model. And this kind of model later informed us to present AI's information in a better way that leads to a higher human-AI collaboration outcome. So for this first project, let's think of this scenario. Well, given a decision-making task, let's say given a profile of a person, and the AI, the decision-making task is to determine, for example, whether this person's income is above a threshold. The AI model gives some kind of recommendation, its prediction, but we can also augment this recommendation by having a language model to analyze how each feature of this task may have contributed to the AI model's decision recommendation, right? So you can see an example here. The AI model is analyzing one particular feature, in this case, the education of this person, and try to see how the value of this feature in this particular case increase or decrease the chance of this person making an annual income over 50K. So if this language model is actually the model that provides this decision recommendation, you can pretty much see this analysis that it generated as the explanation to its own decision recommendation. Now, the problem is, given a decision-making task, you probably have many, many different features that you can have the language model to analyze on and to understand how they contribute to the final decision. So how should we present all this analysis to people in an effective manner? Right, so we started from two very naive and straightforward approach. The first one is we just sequentially present this analysis at random. At each time step, we randomly pick a feature for language model to analyze, and it shows the analysis to people. People can react to that analysis by saying, I agree with this analysis or disagree with this analysis. And then we move on to the next feature, which is again randomly selected from the remaining set of features. So this is our first way to present the analysis sequentially at random. Another very naive way is let's just have language model analyze all the features and present all the analysis at once concurrently to people. And to figure out whether these two ways of presenting the information is helpful or not, we carried out a human subject experiment. And as you can see here in this slide, we find that no matter whether we are talking about income prediction task or recidivism prediction tasks, having this language model analysis being presented either sequentially or concurrently doesn't really help the human decision makers to achieve a higher level of decision-making accuracy compared to the control condition in which we just don't show any of this analysis at all. So this really urges us to think about, this additional information. Presumably, it should be helpful for people to understand whether the AI's recommendation is trustworthy or not, but it's not achieving its intended purposes here. So how should we intelligently present all this information in a smarter way? That is a question that we want to answer. And to answer that question, we started by, as we said, modeling how human will react to different language model analysis presented to them. So we assume that we can use a hidden state to capture humans' mindset or status as they consume a sequence of language model analysis. And what we are doing here is essentially at the very beginning of this interaction, the human's initial hidden state is only decided by the decision-making tasks that they see and the AI model's prediction that is presented to them. And as time goes by, they receive more and more, language model generated analysis. In each time step, they receive a particular language model analysis on a particular feature. This is RT. And they also have some opinion towards this analysis. This is recorded as AT. They either can agree with that analysis or disagree with that analysis. And finally, we say that at the end of time T, we will update this human decision maker's hidden state. And this updated hidden state is decided by their hidden state in the previous time step, as well as the analysis they received at the current time step, as well as their altitude towards the current analysis that they received. And finally, at the very end of the interaction, eventually they need to make a decision, right? So we assume that the human's final decision is influenced by owning their last hidden state in the last time step. So with historical data of how humans actually receive different sequences of analysis and how they eventually make the final decisions, we can actually learn the parameters for each one of these models. And this also means that in the runtime, if we have a particular human decision maker, they have interacted with this language model analysis for a certain number of rounds. We collected their interaction history in terms of what analysis has been presented to them and their reaction to it. We can actually estimate the human decision maker's hidden state at the beginning of time t, and that will be a distribution. We refer to this distribution of hidden state at the beginning of time t as state belief. This is denoted as BT. Okay, so now, the question becomes at the beginning of time t, right? We know this human decision maker, their hidden states, the distribution of the hidden state is characterized by BT. And we have a set of remaining features that language model has not analyzed yet. So the question becomes, among the remaining features, task features, which one we should have language model to analyze and present the resulting analysis back to the human decision maker. And to answer that question, we decomposed it into two steps. The first step, we really want to figure out what is the objective here first to present yet another analysis back to human decision makers. And this actually comes down to that, if we show people different analysis, that potentially will nudge human decision makers into making different decisions. So answering the question of, what is our objective here essentially becomes ideally what decision we want humans to make on this particular decision-making task, right? So in other words, it's like what decision we want to nudge people into making. And to figure that out, we get a lot of inspiration from this wisdom of crowd phenomenon in crowdsourcing, which essentially says that if you aggregate multiple independent sources together, the aggregated result is likely to be better than each individual result, right? So here we're basically saying that how about why not we just optimally aggregate the AI's decision recommendation on the task instance and humans' independent decision on the task instance, and that humans' independent judgment can be predicted. If we are able to aggregate these two judgments together, likely the combined judgment will be better than either party alone. And luckily, we find that in the literature, there are many different ways that people can actually aggregate humans' independent judgment together with AI's decision recommendation to generate an aggregated decision. So we basically use that kind of method to aggregate this two-party of judgment and use the aggregated decision as the target decision that we want to nudge human decision makers into making. Okay, so now we have some idea about what is the direction that we want to nudge people into. The next step is to evaluate, how much do different analysis will actually nudge people into taking that target decision. And to quantify this, we first defined the immediate utility to show a particular analysis R given the decision maker's current state belief is BT. So I'm not going to go into the mathematical details of this formula, but essentially this immediate utility is trying to characterize the probability increase for the human decision maker to take the target decision once we show them this analysis R and we ask them to make a decision immediately. But notice that we don't necessarily need to have our human decision make a decision right after we show them this analysis. If showing them more analysis actually will nudge them to take this target decision even more, we should do that, right? So as a result, we define this overall utility, which is composed of two parts. The first part is the immediate utility, is the same thing as we show you in the first line. And the second part is a maximal future utility. So this is essentially the maximal possible probability increase for the human decision maker to select the target decision if we assume that in all future time steps, we're going to use the optimal policy to determine which analysis to show to people. So in the end of the day, how do we decide which analysis to show to people? We'll basically pick whichever analysis that maximizes this overall utility, and we'll use that one and show that analysis to our human decision maker. So to evaluate whether this algorithmic approach actually is helpful or not, we again carried out a human subject experiment. And as you can see here on this screen, sorry for this small font, but this little star is our approach, and all the other symbols are the baseline approach, and I'm showing you the accuracy, the final decision-making accuracy of the human decision maker. And you can see here that when we use our algorithm to choose which analysis to show to the human decision maker, we're able to significantly increase the human's final decision-making accuracy over a number of baseline where we don't show the analysis at all, or show the analysis at random, or show the analysis all at once. And we also outperformed another baseline, a heuristic baseline, in which we just determine the order of showing this language model analysis based on the feature importance of each feature. And a closer look into the data basically suggests that this increase in final humans' decision is mostly caused by their decrease of over-reliance on AI when AI's decision recommendation is wrong, and it doesn't significantly influence their reliance on AI when AI's decision recommendation is correct. Okay. So that's our first project. We try to model how human will react to different information presented to them, and then try to determine correspondingly how to best present information to human decision maker. Now, very quickly, let me give you some idea about a second project in which we try to model how human will adopt AI model's decision recommendation, and how that model enabled us to change what kind of recommendations will be presented to humans. So essentially, if we think about how AI models are trained today, you will realize that AI models are trained today for its own performance, right? We try to minimize or optimize this loss function, and this loss function is just comparing AI's own performance against the ground truth. So in that sense, this kind of optimization procedure effectively ignored the role of humans in this collaboration process. It could be that AI is super accurate on some task instances, but the human will not following the AI's recommendation there. But when human really needs some kind of AI recommendation, AI's performance may be super poor there, right? So this kind of behavior oblivious AI model training is really ignoring the role of human in the process of generating the final human AI collaborative decision outcome. So the key question here is that how can we actually train the AI in a way that really accommodates humans' needs and behavior? And our proposal is that instead of training for the behavior oblivious AI model, we should train behavior aware AI model. And this behavior aware AI model, one, it will explicitly account for humans' reaction to AI recommendations in the training process. And then secondly, it will directly optimize for the human AI joint collaboration outcome rather than AI's independent performance. So a key precondition for us to be able training this kind of behavior aware AI is that we should have some models about how humans are actually reacting to AI's decision recommendation. How will they factor AI's decision recommendation into their final decisions? So in one of our recent projects, we take a very simple step towards this end. So we get inspired from some of our empirical observation of how humans adopt AI recommendation, and propose this simple thresholds model to characterize humans' adoption of AI decision recommendation. So this threshold model essentially says that the human, if their own independent their confidence on their own independent judgment is higher than the threshold, they will just go with their independent judgment. But if their own independent judgment's confidence is not high enough, it's below this threshold, they will go with AI's decision recommendation. So this is a very simplified model for how human will react to AI recommendation. But it turns out that under this particular model, the problem of training a behavior-aware AI model to directly optimize for the human-AI collaboration outcome essentially becomes a weighted optimization, weighted loss optimization problem, right? So we will have a weight associated with each of the training instance. And for some particular, scenario, if this confidence threshold tau is known, we can say that the weight associated with each of the training instance is going to be 1 if humans' confidence on that instance is below the threshold. Otherwise, it's going to be 0. But there are also many cases that this threshold may not be known ahead of time. Then we can assume that this threshold is sampled from an underlying distribution, and we also will be able to derive the optimal format of this weight for each of the training instance. And the intuition here is still, if humans are more confident about their own independent judgment on a training instance, that training instance should get a lower weight in the training process. And to test out whether this kind of behavior-aware AI model indeed can help improve the human-AI collaboration outcome, we carried out another human subject experiment. So we carefully curated a subset of images from ImageNet. This subset includes 5 typical object classes, which are relatively easy for people to classify. And we also include 5 relatively challenging dog breed species classes in this data set. So we are asking our human subjects to participate in the image classification task as the decision-making task. What you will see here is that we trained 2 models. We trained one behavior-oblivious AI model following the traditional method, just optimizing for its own independent performance. But we also trained a behavior-aware AI model using the human confidence-based weighting strategy, as we just explained to you. And as you can see here, compared to those human participants who are collaborating with the behavior-oblivious AI model, which is shown in the red bar, those participants who are collaborating with behavior-aware AI model actually achieved a significantly higher accuracy in their final decisions. And when we dive deeper into the data, what we will find is that for this behavior-aware AI model, they will increase their performance on those cases, on those classes that are relatively challenging for people to classify, that are the cases that human will have a low confidence in. So they improved their accuracy on the dog species, but at the same time, as a price, they decreased their the accuracy on those cases that is relatively easy for people to recognize. And this is especially salient for some class of images like this dingo dog species and the gas pump. But if you look at, so what I'm showing you here right now is just the AI model's performance, right? But if you look at the final decision-making accuracy made by the humans, once they receive the AI recommendation, what you see is that for the dingo dog species, for images belonging to this dingo species, their final accuracy when collaborating with behavior-aware AI model is significantly improved because the AI itself has a better performance there. But when we look at the gas pump, right, the human decision makers who are collaborating with AI are not decreasing their final accuracy on gas pump, because on those cases, they just didn't really rely on AI. They just used their own judgment to fill in the gap. Okay, so so far, I've told you about 2 example projects in which, through modeling the interaction dynamics between human and AI, we successfully improved human-AI collaboration outcome in decision-making. But I just want to, before I wrap up the talk, I just want to briefly mention that the same methodology could potentially be adopted by adversarial parties to undermine human-AI collaboration, right? So, for example, in one of our recent studies, we find that, humans' cognitive biases in terms of how they will adopt AI recommendations will actually pose a serious vulnerability for human-AI collaboration. For example, the adversarial parties can quickly destroy humans' trust on AI just by selectively attacking the AI model on those cases humans feel super confident about. And in fact, the adversarial parties can use a model like a hidden Markov model to characterize how exactly humans' trust and reliance on AI will change over time. And making use of this model, they are able to strategically deploy their attacks on the AI models in a way such that they can maximize the reduction of human-AI collaborative decision-making performance while with minimal attack cost. Okay, so that's all that I want to share with you. Just a few, I hope I have already convinced you that modeling the interaction dynamics between human and AI can be a fruitful research direction for promoting human-AI complementarity, but we also should be mindful about that adversarial parties can use the same techniques to undermine human-AI collaboration. Thank you.